Okay, dear students, this is going to be the lecture 4 of the course MTH 803. That's the basic course on Fourier analysis. So last time we defined Fourier series and did some result, and we had reached a point where we proved that if AN and BN are the Fourier coefficients of a function f, that is, say, Lebesgue integrable on an interval minus pi to pi, then limit an as n approaches infinity is equal to 0, which is the same thing as limit n approaches infinity bn, where a and bn are defined as you know already know, 1 by pi minus pi to pi fx cos nx dx, and bn is again 1 by pi minus pi to pi fx sin nx. Okay, now we move a little ahead. Now we know that we are looking for the conditions for convergence of the series 1 by 2a0 plus summation an cos nx plus bn sin nx, the Fourier series generated by f. Okay, now one thing that we now know that you know, for the convergence of a series, it is necessary that the individual terms converge to 0, which is the case here because cos nx, it is finite, whatever n, and of course a and b, and if they converge to 0, so there is certainly should encourage us to investigate whether the series, under what conditions does this converge, this series converge, and for what values of x. So one thing is encouraging, that we know that a and b and do converge to 0 as n approaches infinity. Now from this we can deduce that now this would be a remark to our previous theorem, that if phi is a Lebesgue integrable function on any interval ab, then limit n approaches infinity a to b for any interval phi times cos nx dx is equal to 0, and similarly limit n approaches infinity a to b phi into sin nx dx is equal to 0. Of course, we are going to use the previous theorem, and we know that Fourier coefficients as n approaches 0, as n approaches infinity, become 0. Now let's deduce this. Now this is again a little bit of calculation. Okay, now we can always now you have to remember that ab is some arbitrary interval, but we can always find an integer m, right, such that a and b lie between minus m pi and m pi, right? Of course a is less than b. So we can always find this m belonging to a set of natural numbers such that this is true. Okay, so what we do, we extend this function phi, which was Lebesgue integrable, or basically was, we only know its values on the interval ab because it is defined on ab. So but we can extend it, like we can define f of x to be phi of x in case a is less than, x is less than equal to b, and it's equal to 0 at all for all x belonging to minus m pi, and you take away the interval ab. Now on the remaining points it is 0. So then f indeed belongs to the Lebesgue integrable function on the interval m pi to m pi. And we can do it further. We can then define g of x to be f of mx. Then g becomes a Lebesgue integrable function on the interval minus pi to pi. That can be easily checked. And then, as is the usual thing, we just define g of x plus 2 pi to be g of x. Then we get g belongs to Lebesgue integrable function, and g is a periodic function now. it repeats its values on minus pi pi, and it is Lebesgue integrable. So having done this much, okay, so if I look at the limit that I had to evaluate, that is I have to evaluate this thing. I have to show that this is equal to 0. Now then a to b integral phi cos nx, I take this one, the same would apply to the second one. Okay, dx can be written as minus m pi to m pi fx cos nx, because fx is phi between a and b, and as the rest of, okay, on the other value, on the other points on this range, it is 0. So then you just put x equal to mu. By that substitution you will get it m times minus pi to pi f of mu cos of n times mu du, right? But f of mu is the same thing as g of u, of course, minus pi to pi g of u cos nm times u du. Okay, by just making a substitution, right, we get here. Now after that it's straightforward. Now g is a periodic function, and I can apply, and then this just the Fourier coefficient of g, that is, it is pi times m into amn. Now which would approach 0 as n approaches infinity. Now we already know Fourier coefficient goes to 0 as this index goes to infinity, and for a fixed m, as n goes to infinity, then mn would go to infinity. It means because m is fixed, it would depend upon our fx, where does a and b lie, which are fixed. So similarly this would be equal to 0. Now for any integrable function, limit n approaches infinity, a to b phi cos nx dx is equal to 0, and limit n approaches infinity, phi times sin nx dx is equal to 0. It's a simple evaluation, you can do it on your own actually, shouldn't be difficult. Now from this we can deduce, now there is an important deduction from this, and that would be that limit n approaches infinity 0 to a, okay, now we are assuming that, okay, phi times sin nx by x dx is the same thing as limit n approaches infinity integral from 0 to a phi times sin nx divided by x. Oh, just a minute. Okay, right, here it is sin of x. I thought I made some mistake. Okay, dx. These two integrals are essentially the same, provided phi belongs to the Lebesgue integrable function over minus pi pi, and of course 0 is a positive number that is less than pi. Now this can be deduced from our earlier result. Now remember that now this is, now if n approaches infinity, you have got here sin nx divided by sin x, and on the right hand side you have got sin nx, and you can as n approaches infinity, the limit would be same if you replace this sin x by x. Now this is going to be important in our deduction, in our the theorem that we are going to do at the last, that is the Dirichlet's criterion for the pointwise convergence of a Fourier series. Now what we do, if we take this function 1 by sin x by 1 by x, right? Now this is indeed defined in continuous provided that x is not equal to 0. But if I define f of x to be this function, and I define it to be 0 at x equal to 0, you can see that this function becomes, now then this fx, if in case x is not equal to 0, then this fx is indeed, f is continuous on the closed interval 0 to a. However, this can be easily checked using L'Hopital's rule, no issues, because as x approaches You can do it by L'Hopital's rule, do it yourself. Okay. So that means if now phi is an integrable function, phi, now since this is continuous, then this function phi into sine x minus 1 by x is an integrable function because this function is continuous. Then this, because phi is given to be a Lebesgue integrable function, this product is also a Lebesgue integrable function because this function is continuous on the interval 0 to a. Okay, which we know now, if you have an integrable function, then you by the previous remark, then this would imply limit n approaches infinity 0 to a phi into 1 by sine x minus 1 by x multiplied by sine nx, the previous deduction. Now here the phi can be taken to be this whole function. You just substitute in place of phi into 1 by sine x minus 1 by x sine nx. This is our phi in the previous remark. Now this is 0 by previous theorem, now which would give us our result that limit n approaches infinity 0 to a sine nx divided by sine nx sine x dx is the same as limit n approaches infinity 0 to a phi, again phi is here, which is an integrable function, that's important, sine of nx divided by x dx. Now remember this deduction from what we have done thus far. Okay, by the way, these two integrals are called Dirichlet's integrals that are important in reducing the Dirichlet's criterion for the convergence of a Fourier series. Okay, now keeping this in mind, we prove a theorem. That's again going to be important. Our theorem is the theorem that's given in your notes, right? Our theorem is this: if f is a bounded and integrable function on an interval 0 to a, where of course a is some positive number, and monotonic increasing or monotonic decreasing, whatever, but monotonic in the interval 0 delta, where delta is a positive number less than a, then limit n approaches infinity 0 to a fx multiplied by sine nx divided by x dx is nothing but f0 plus 0 to infinity sine x by x. Now remember that we are taking this out, and it is not here sine nx, it's sine x by x. We know it converges. We also know its value basically. This is actually, what is it, root of pi by 2? We will see that. What is the value? I think it's pi by 2, the value of this integral. So in this way we can actually evaluate this limit. Now what is this f of 0 plus? F of 0 plus is the shorthand for limit x approaches 0 from right f of x. And we write it in shorthand terms f of 0 plus. But you can also replace it by this, no issues. But it would save some space and some time. Proof. We first take the case, now case 1, we would prove the case 1, where we assume that f of 0 plus is equal to 0. That means I am assuming that limit x approaches 0 from right f of x is equal to 0. From this we will be easily able to deduce the general case, right? Now furthermore, we may assume without loss of generality that f at 0 is equal to 0. Now that shouldn't create any problems because we are of course evaluating integrals, and if we alter the value of the function at one point, it does not affect the value of the integral. Okay, now what we do, so if our 0 is less than delta is less than a, there is something called Bonnet's mean value theorem, or the second mean value theorem of the Riemann-Stieltjes integral or the Riemann integral. And using the fact that f is monotonic, and you must go through that. That's a good thing. No, you just check on the net or your notes on some books, the second mean value theorem. By second mean value theorem of Riemann-Stieltjes or Riemann integral, or even the Lebesgue integral, it applies to all the three. You can find all the three. You just do the Lebesgue, that of course it would imply all the other three or the other two. Okay, there would exist a delta 1, a positive number, a delta 1 belonging to the interval 0 to delta, such that integral 0 to delta fx sine nx divided by x dx is equal to f of 0 from 0 to delta 1 sine nx divided by x dx plus f of delta, the upper bound, the upper value in the range, from delta 1 to delta sine of nx divided by x dx. Now this is our second mean value theorem, provided that f is monotonic. Now that is the condition in the second mean value theorem also. Okay, now which can be written as, because I have assumed that f of 0 is 0, so this is basically f of delta into delta 1 to delta sine of nx divided by x dx, which by some change of variables would be f of delta into n times delta 1 to n delta sine of t by t dt. Okay, now remember this. Okay, I just move ahead. Now we know that, as I already said, now you have done this in your first course in analysis, surely. In your first, somewhere you must have done it, that 0 to infinity sine x by x dx is convergent. So, implies that, convergence implies this, that there exists some k positive such that for all x, it must the greater than or equal to 0, modulus of 0 to x sine x by x dx is less than or equal to k. And let me make it here some lambda, so that, okay, so there exists, so this thing is bounded because I don't want to get it confused with this x. So which would imply that n times delta 1 to n delta sine x by x dx, which can be written as modulus of 0 to n delta sine x by x dx, then minus 0 to n delta 1, just how we sum up the integrals, sine x by x dx. And now using the triangle inequality, this would be less than equal to 2k by this reason. Okay, also I have assumed that f of delta approaches to 0 as delta approaches, which is the same thing as I have assumed the case 1 is about f of 0 plus is actually f of 0. So which implies that, now this would imply for any epsilon positive, since it is becoming 0, I can make it arbitrarily small after a certain stage. There must exist some gamma positive such that f of delta can be made smaller than any positive number, in particular epsilon by 4k, where of course I am dealing with 0 is less than, delta has to be less than gamma, but it is still bigger than 0, which would imply 0 to delta f into sine nx by x dx, it is nx here, modulus is less than equal to f of delta times 2k, but f of delta, as delta approaches 0, once it is very very small, is less than epsilon by 2. You are using that this is less than epsilon by 4k. For 0 is less than, delta is less than gamma. Now this is because of we have used this condition, right? Okay, now getting to where we were, I write it as, now I have to evaluate this. I have to show that 0 to delta fx sine nx by x dx is equal to 0 to delta f times as sine nx by, I can just break the integral into 2, plus delta to a fx sine nx by x dx. And observing that delta to a fx into sine nx by x dx is 0 approaches 0 as n approaches infinity. Now that's by our remark, because in this range, because delta is a positive number, 0 doesn't come into picture, so fx by x is an integrable function, because f is an integrable function. And using that remark that we did at the beginning, this would go to 0 as n approaches infinity. It's an integrable function in this range from delta, because delta is above the 0. Okay, so in the range from delta to a, this is an integrable function, therefore this must go to 0 as n approaches infinity. If something approaches infinity, it would mean that there exists some m belonging to the set of natural numbers such that this thing can be made arbitrarily small, right? So that means now we already know that 0 to delta fx sine nx by x dx. By the second mean values theorem, we know that 0 to delta, this thing is less than epsilon by 2. But this thing is converging to 0 as approaches infinity. So this is less than epsilon by 2. This becomes 0 as n approaches infinity. So after a certain stage, this second integral must be less than any positive number. In particular, it must be less than epsilon by 2. So that would mean there exists some natural number m such that 0 to a fx sine nx by x dx is less than epsilon by 2 plus epsilon by 2, which is less than epsilon for all n bigger than or equal to m. So which would automatically imply that limit n approaches infinity, 0 to a fx into sine nx divided by x dx is equal to 0. So this proves the case of our theorem. What was our theorem? Our theorem was that this is equal to this thing. Now case 1 is that f of 0 plus is 0, so this right hand side is 0. So that's exactly what we have proved. So this proves the case in case f of 0 plus, that is the limit of fx as x approaches to 0 from right, is equal to 0. So that case is solved. Okay, now we take the case 2, in case f of 0 plus is not equal to 0. Now in case f of x, f of 0 plus is not equal to 0, in that case, now in general case, or in case f of 0 plus is not equal to 0. So what we do, now since we know that limit x approaches 0 from right, f of x minus f of 0 plus is indeed 0, because this is just some number, because the limit exists, right? And of course this is the same thing. Okay, so we can just replace f by f of x minus f of 0 plus and apply the case 1. So that would mean by case 1, limit n approaches infinity, 0 to a f minus f of 0 plus multiplied by sine nx divided by x dx is equal to 0, which would imply, by distributing the limits, that limit n approaches infinity, 0 to a f, of course यहाँ पे f of x है, f of x sine nx divided by x is indeed equal to f of 0 plus limit n approaches infinity, 0 to a sine nx by x dx. Now again we just make a, what is that, change in variable. So this would be limit n approaches infinity, 0 to na sine t by t dt. Just put nx equal to t. Now this is the same thing as f of 0 plus 0 to infinity sine x by x dx. Okay. Now, one thing we know that from elementary calculus, this is equal to pi by 2. This integral, this improper integral 0 to infinity sine x by x converges, it converges to pi by 2. So we can just substitute the value here and evaluate this integral in case f is monotonic. Now, you have to remember that. Okay, from this we can evaluate, we can prove another theorem. We can just go ahead and prove that let me do that theorem. Now after that we will go to the Trickle's criteria. The theorem is, if f is bounded and integrable in the interval minus pi pi and monotonic in minus delta to 0, of course 0 is not included, and 0 to delta, where 0 is less than delta is less than pi, and within a subinterval here minus the 0 is the function is monotonic. Of course it is integrable and bounded, and of course it need not be in the same sense. It could be that it is monotonic increasing in this part and monotonic decreasing, and vice versa. So it is monotonic but not necessarily in the same sense. Then 1 by 2 a naught plus summation n runs from 1 to infinity a n is equal to f of 0 minus plus f of 0 plus divided by pi into integral 0 to infinity sine x by x dx. Now again, what is f of 0 minus? It is nothing but limit as x approaches to 0 from left, f of x, the shorthand for this. Okay, so this is what we are going to prove. And you know what is AK? AK is just the Fourier coefficient. AN is the Fourier coefficient. You know that 1 by pi minus pi to pi f of x cos nx dx. I hope I am using a different pen. I hope it's visible. I will try my best because the ink of that black pen is gone. Now it's very easy to do. It is just a simple thing. Using the previous theorem, it should be easy. 1 by 2 a naught plus summation k runs from 1 to n a k is equal to, by using this formula, it would be 1 by 2 pi integral minus pi to pi f dx plus 1 by pi integral summation k runs from 1 to n minus pi to pi fx cos kx dx. Okay, now then this would be further equal to it. We can just write it simply as 1 by pi integral minus pi to pi f into 1 by 2 plus summation k runs from 1 to n cos kx dx. Now we know what this is equal to. We already have evaluated this while evaluating that Fedger's and Trickle's kernels, that this thing, this expression f is basically sine of n plus 1 by 2 times x divided by twice sine x by 2. So that is a simpler expression for it. Now what we do, we just evaluate it from, we can just break it into 2. So then it would be equal to, taking this 2 out, I can just break it into 2 and I can write 1 by 2 pi from minus pi to 0 f into sine of n plus 1 by 2 times x divided by sine x by 2 dx plus, of course, 0 to pi f into sine of n plus 1 by 2 dx, of course, divided by sine x by 2. Okay, this is what you have done. Now by some straightforward I want to finish it. Okay, this is where we have reached. We can write it further as 1 by 2 pi. You just put in the first integral, you put x equal to minus x, and note that sign of minus x is minus x, so minus minus would cancel here. So it would be basically 0 to pi in the first integral will become f of minus x. This won't be affected because in the denominator and denominator minuses would get cancelled out. So it would be sine of, let me write it as n plus 1 by 2 x divided by sine x by 2 dx plus 0 to pi f of x sine of n plus 1, the same thing as the previous. I shouldn't have written it. Okay, now then it can be further written as, you just put x equal to 2t. So if you put x equal to 2t, you will get 1 by 2 pi twice 0 to pi by 2 f of, put x equal to 2t, so it would be minus 2t sine of 2n plus 1 into t divided by sine of t dt in the first integral, plus keep it as it is, no change here also, of course. It would be 0 to pi by 2 f of 2t, of course the same thing, sine of 2n plus 1 t divided by sine of t dt. Of course this 2 has to come out, so that would imply that's what we wanted. So this is basically, of course 2 cancels out, 1 by pi 0 to pi by 2 sine of 2n plus 1, oh sorry, what's this? This is 1 by pi. Now of course here on the right hand side we have got a0 by 2 plus summation k runs from 1 to n, ak is 1 by 2 pi. Take these two integrals and remember the previous theorem. This is 0 to a, think of pi by 2 as a, right? And we know that sine 2n plus 1, as n approaches infinity on the right hand side and I let n approach infinity on the left hand side, it would, so it would be k runs from 1 to infinity if I let, or let me write it like this, n, and limit n approaches infinity would be limit n approaches infinity 0 to pi by 2